We will move to the next presentation. This is from Kevin Non, who is Vice President Technology and Marketing at leading paste maker DKEM. So he will tell about the key developments in metallization paste solutions for TOPCon. Kevin, the floor is yours.
Okay. Let me share my screen.
Yeah.
Okay, can you see my screen?
Yeah. You have to go into the presentation mode.
Okay.
All is well.
Okay. I think it's a great honor to have this talk again, following last November's speech. Today, I also want to talk about something about TOPCon solid cells metallization. Also, in this speech, I would like to highlight something about selective emitter progress in industry. Okay, this is quite a brief introduction of DKEM. DKEM is actually the Chinese company. We founded in 2010, and we are working on high performance electronic materials. So far, we focus on two business areas. First one is silver paste for photovoltaic solar cells, and the other one is electronic adhesives for semiconductor electronics. In 2020, DKEM became the first Chinese company, listed company in silver paste sector. Right now, we are in the leading position in photovoltaic metallization, especially in the TOPCon metallization sector. This page gives a brief introduction of DKEM's technology roadmap for photovoltaic metallization and interconnection. Actually, we are working with PV industry from 2014. If we look at the untapped solid cell sector, we started to work with customers on unpaired solid cells from 2017, and for the TOPCon solid cells, we work with a very leading customer like Jinko Solar from 2019. From that time, we work closely with industry leading customers and develop our metallization solutions. Right now, we can give a total solution, a passive solution for TOPCon front side metallization and the back side metallization. Here we just want to which kind of customer we are working with. We work with the very leading TOPCon customers and also the wrapping up capacities. Right now, I think DKEM holds more than 50% market share at TOPCon metallization sector. So we are looking forward to working with different customers. So we go to the main page. This page, we would like to analyze what as a passive supplier, what can we do to serve the TOPCon customers, to help customers to increase the solar cell efficiency while achieve lower cost. At the right side of this page, we utilize the literature picture. Here shows some power loss analysis. Actually, we here divided into three parts. First one, the green part is for front side power loss, and the blue one is back side power loss. For DKEM, since we are a paste supplier, so we are trying to link what we can do to the power loss. So we can also work from three sectors. First one is for the front side is the key. I think is efficiency accelerator. Is a key enabler for higher efficiency of TOPCon solid cells. The biggest issue for front side is still the metallization recombination. For this one, we can work from both paste and emitter design part to improve it. The second one is also still the emitter recombination. Here we can use the higher sheet design or use the selective emitter design to help to improve. And for the paste, contact resistivity is still the always need to be as low as as low as possible. So for this part, we can also improve from paste or emitter design. Then we still need to reduce the grid line resistance to enable fine line printing. And also, for optical loss, we need to reduce the shielding. We need to print with narrow finger opening. This year, I think we can work with customer with less than 13 micron finger opening. And for backside, this year I think it's a cost booster. We give more attention on cost saving at backside. First one, try to reduce absorption. We need to enable a thin polysilicon layer, and we also need to reduce the passivation recombination. Here we need to combine with alkaline polishing surface condition. And for the metallization recombination, we need to do it as good as possible. And for the contact resistance, it's quite complicated for the TOPCon backside, since there's alkaline polishing and also sometimes have the aluminum oxide condition. So we need to pay more effort on this part. And for green line resistance, is quite related to low laydown request. Also, either from paste itself, or we need to work with customer to enable a fine line printing less than 15 micro this year. And also we would like to try lower solid design for backside to achieve lower cost for backside metallization. So generally, I think metallization is actually the key enabler for TOPCon technology. And from this analysis, we can see that p-type emitter metallization is actually very critical for TOPCon efficiency improvement. As to DKEM, as I just highlighted, we have the total solution. We have front side DK70 or 71A aluminum silver paste for finger, and we have DK81A for bus bar. For backside, we have DK93T for finger and DK91A for bus bar. This is a general introduction for what we can do. Next one, we just want to highlight how to make a contact to TOPCon solid cells. First, we need to work with backside and plus polysilicon, and we also need to make good contact with the p-type emitter. So for n-type polysilicon, or either for the n plus emitter for PERC solid cells, we need to form as much as the direct conduction channels. That means the more silver crystal around the pyramid tips. To this kind of direct conduction is very effective. Others we may know there is also indirect conduction channels. But if we look at the efficiency of conduction, direct conduction dominates over indirect ones. So then we look at what happened at the p-type emitter. For p-type emitter, it's a boron doped surface. Is there compared to the n plus emitter? For the boron doped p-type emitter, for the surface there is lack of electron. It's difficult for silver ions solved in the molten glass during firing to reduce to form the silver crystallize, which work as the direct conductions. So what we need to do is to help to promote the formation of direct conduction to p-type emitters. So right now for the industry, we are always use try to add some aluminum powder in the silver paste. With the aluminum powder incorporation, something changed. You can see from the right pictures that during firing, the melted glass. First, we'll etch the silicon nitride and aluminum oxide stack layers to create some local holes for material exchange between the liquid silver aluminum phase and the silicon in the emitter. By any of these aluminum powders, it's easy to form the low melting point silver aluminum phase. And finally, the big size silver aluminum spikes formed in the emitter or even penetrate into the silicon base, which will take the role of direct conduction channels, which to help to achieve good contact. But unfortunately, this kind of design will cause severe metallization induced recommendation. We need to take care of our recipe of formulation design to get a balance between the contact improvement and recommendation. This page shows how paste suppliers can control the or optimize the contact and recommendation on conventional P-type emitter. Generally, we can modify our recipe to control the formation number and size of silver aluminum spikes by modify our glass phase design and our aluminum selection. So basically, we can use optimize our glass etching property to create more local holes for material exchange channels, and then we can optimize our inorganic formulation, try to control the thermodynamic of a spike growth to form smaller spikes. That means we would like to see smaller but more numbers of silver aluminum spikes to get a balance between contact and recommendation. Besides to silver paste itself, we can also utilize the process optimization to improve the performance. First, we can design deeper junction or use selective emitter to weaken the impact of silver aluminum spikes. And also we can optimize our firing profile, try to get lower thermal flux during our firing to control the thermodynamics. That means we can try to use optimize our firing profile to achieve smaller but more numbers of the spikes. This page, we talk more about P-type SE emitter. Here we just focus on the laser doped P-type SE emitter. Actually, for SE emitter, it's actually a combination of the current regular conventional designs. At the non-metallization area, we can get even shallower emitter. And while for the metallization area, by the advantage of laser doping, we can achieve very deep junction, but maintain a reasonable surface concentration. With this kind of junction design, it's easier to get very low emitter recommendation. While as I just said, we for metallization area, it's much deeper junction, so it's easier to achieve lower general metal. It's good to the metallization recommendation. And also, you look at the middle pictures, you can see that for the deeper junction, it's also easy to get a lower contact resistance. So it's pretty good for a metallization design. So with this kind of SE emitter, it's easier for customers to achieve more than 0.3 finishing benefit combined with metallization paste modifications. And also this kind of deep junction at metallization area is also good to achieve robust reliability. But still some challenges, because we always see that after the laser SE processing, there's some damage on the texture, especially on the pyramid tips. After the laser treatment, there will be a higher reflectivity. Also, this kind of damage impact a lot on the following metallization performance. So for laser doped SE, we need to optimize the laser process as the first step. Then we can try to optimize our paste to achieve even better performance. If you look at the SE pictures on the front, you can see that if the paste is not well optimized, as the traditional, we can see the traditional silver aluminum spikes. Besides this, we also see some even very obvious parameter damage happen. Here I marked as the orange circle. But after the paste optimization, here we have the new generation of DK71 paste. With this kind of paste, we can see the traditional spikes, but without the damage on the parameter tips. So with this kind of new design for paste, we work with customer combined with the pattern optimization. It's easy to achieve more than 0.3% efficiency gain, and we are confident to demonstrate more 0.3 to 0.5 efficiency gain with whole process optimization. I think this is achievable in this year. And right now, DK71A has already become the benchmarks for most TOPCon SE customers. From this page, we talk something about the backside. For backside, as I mentioned before, it's quite complicated because for front side, we have different ALD aluminum oxide machines. Some have backside wraparound, some no wraparound. And even for the special customers, they prefer the whole surface, whole backside surface have the aluminum oxide. It makes the contact difficult. And also for backside, we have LPCVD type machine, which prefer alkaline polishing surface and backside. Some is the PECVD type machine, which prefer the small texture design and backside. So this makes the backside contact quite complicated. We need a very wide window paste, either to the contact window or the firing window and the EL window. It's good that the DK93T silver paste with the innovative glass chemistry delivered a pretty good contact performance, and we worked with about 4 kinds of conditions. Demonstrate very strong performance and window. Right now is actually the benchmarking product in the industry. This page, we want to pay attention on the low cost. For backside of TOPCon, for finger design is always wider than front side. So as a result is that backside laydown is always higher than front side. So it's a bottleneck to lower cost. So this year we would like to design lower solid contact backside silver paste. Here is a demonstration of our 2 or 3% lower solids version is DK93T-L. This kind of low solid design has already been confirmed very good performance at leading customers. So at this design, the difficulty is that we need to maintain a good efficiency while to deliver very excellent yield. It's easy to do the low solids, but it's difficult to maintain the contact performance and the efficiency. This is what I have done. We modify our glass and the silver combinations, also optimized our finger morphology. So we achieve this very good data. We would like to promote this kind of low solid concept this year to promote the lower cost request. Okay, this page we touch upon the ultra thin polysilicon layers. Actually, I think every customer would like to do some thin polysilicon layers, but right now the reality is that in the industry, most of the customer still in the 120 nanometer, around 120 nanometer. Why we can achieve we can to do the thin polysilicon layer. From this page, we can see that if we do a thin polysilicon layer, a general matter increased, a contact resistivity increased. So it's a big challenge for metallization. To us, we did some studies that with thin polysilicon layer, the sheet resistance increased significantly, and also we learned that there is some barrier effect for tunnel oxide layer to phosphor, which will make it difficult to contact for ultra thin polysilicon layer. So at DKEM, we also implementation R&D side to optimize our paste. So far we can deliver both low recommendation while low contact backside zero paste. For to DKEM, I think we are quite open to work with customer to customize their paste for their special different backside conditions. To us, I think it is critical for industry to go to less than 100 nanometer polysilicon. Okay, well, here we go to the last page. It's a summary page. As I mentioned, I think metallization innovation is actually the enabler for the industrialization of TOPCon solid cells. And for front side AGL paste, it is, I think we need to focus on the efficiency improvement. And I think combined with the SE type emitter, we are confident to deliver 0.3 to 0.5% higher efficiency with robust reliability. And for backside, as emphasized, it's critical to lower costs. I think from paste part, we will design low solids concept, and for customer, they would like to achieve even thinner polysilicon layer. So overall, I think DKEM right now in the very leading position and for TOPCon solid cell metallization. So we are committed to deliver our total solutions to help customer and the industry to achieve more than 26% efficiency for TOPCon solid cells in this year or early next year. Okay, that's all on my part.
Thank you, Kevin. Thanks a lot. I think it looks like a really very deep, in-depth knowledge on metallization. So I have one quick question. I really want to catch up with the timings, but can you tell us what's the laydown on the TOPCon right now, the average in the industry, and what's the reference to the PERC?
Okay, if you look at your consumption per watt for PERC, if we include the front side zero paste and backside tapping, it's around 10 milligram per watt. This is for PERC. For TOPCon right now is between 12 to 13 milligram per watt. If you look at the laydown for single solid cells, for TOPCon M10 size wafers, right now is between 95 to 100 milligram for leading customers. While for PERC, I think less than 80 milligram.
Okay. Great. I think there are a few more questions in the chat box, and it would be really great if you can just stay and answer them.
Yeah, for sure. Thank you.
Okay, great. Okay, thanks, Kevin. Thanks a lot.